Welcome, everyone. The Society of Petroleum Engineers Drilling Advisory Committee is pleased to present this virtual seminar, Computational Fluid Dynamics and Real-Time Data Analysis, Assurance and Efficiencies on Cement Jobs. Please note that this call is being recorded and all lines are muted. If you need help at any time, you can send us a message in the chat box. Today's presentation will last up to 90 minutes, and there are 3 parts, and we will take questions after each one. So get your questions in early. Simply type them into the chat box in the lower left corner of your screen, and then click on the send button. There are also poll questions throughout the presentation. When a poll question appears, simply click on your screen in the box next to the answer of your choice. I'm now pleased to introduce our moderator. Dr. Andrea Koesters did a PhD in fluid flow at the University of Cambridge, UK. She then joined the drilling technology team at BP, where she focused on real-time data and drilling optimization. She recently went traveling for a year and is looking after the webinars for the SPE Drilling Advisory Committee. Andrea, welcome to the program.
Thank you, Jill. I would also like to thank the SPE Foundation for sponsoring this web event, and now I'm pleased to welcome our speaker. Dr. Paolo Gomes graduated in chemical engineering and obtained a PhD in fluid dynamics from the FEUP, the Faculty of Engineering of the University of Porto in Portugal. After a short spell in process consulting at BHR Group, Paolo joined BP and the upstream technology drilling team in London in early 2012 as a drilling modeling engineer. In 2016, he took on the role of cementing specialist. Also, since 2015, Paolo has been an invited lecturer for drilling engineering at the Master Science course in Petroleum Engineering at the University Nova de Lisbon in Portugal, in partnership with Heriot Watt University in Scotland. Paolo's research interests are on developing models for real-time data analysis for drilling operations and their field deployment, and computational fluid dynamics applied to wellbore conditions. Welcome, Paolo, and over to you.
Hi, thank you, Andrea. Thank you, Jill, for the kind introduction. And thanks also to SPE for the opportunity to share some of the exciting work I've been involved with for the last few years. And I also would like to extend my thanks to everyone in the audience who took the time to dial in today. A warm welcome to you all. So the theme of this talk will be focused on data. Data needed for the job design and data needed data being streamed during the job execution. I will be talking about 2 main tools, computational fluid dynamics, or CFD as I will refer to it from now on, and real-time data analysis tools. I'll be showing some examples to support some of the findings that we have using these tools, and some of the strategies as well that we implement on a day-to-day basis. I really hope you enjoy the talk, and I hope it triggers also some interesting discussions. But before we proceed, I would like to find a little bit more about yourselves. So if you could please just select from where you're dialing in, from the options available there on your screen, I would appreciate that. Now I realize that perhaps I should have an entry there for Portugal, my home country. I hope some colleagues and friends are dialing in. So thank you for that. So there's quite a few dialing in from the United States of America. So good morning to you all. Some here in the UK where I'm based as well. Good afternoon. Middle East, good evening. And I hope the rest of the world also fits in one of these. I hope no one is dialing in during the night. Moving on, another question for you. Which one describes best your current role? So again, if you could select from the options available. This takes a bit of time to update with every answer. So we see some academic participants, consultant second, and service providers third. So funny enough, no operators on the line, or operators didn't bother to click on the option A. We'll find that out during the call, I hope. And then last question for you. What type of modeling tools do you use the most? Software from service companies, FEA and or CFD? You develop your own algorithms and models, or none of the above? Okay, so far a good distribution here. I encourage you to answer those questions. This is a way of knowing that, of me knowing that someone is out there as well. I hope this is a representative. So a big participation here on software from other companies, and then a split between CFD, FEA, and own models developed. Thank you for that. That gives me a bit of a background to who am I addressing today. So the webinar will be split in 3 main parts. But before that, I will just cover some introduction on the challenges that we face in a day-to-day basis. And then, as I was saying, there will be 3 parts to this webinar. On the first part, we will be talking mainly on job design and how computational fluid dynamics can help us on that part of the work. On the second part of the call, we will be focusing on real-time data analysis. And then on the third part, I would like to share my vision for the future. I would like to share some ideas and concepts on how these two connect the real-time data analysis and the preparation for the job. So let's start the presentation by introducing some of the challenges here. And I would say that the main challenge in drilling nowadays could be perhaps split in 2 big groups. Some of them are physical challenges, some of them are in the domain of the digital and data. So, for example, in the physical aspect of it, drilling is still something that it's hardware-based, something that is hands-on, and therefore we rely on challenges such as the pore pressure fracture gradient of the rock to drill ahead. We need equipment that delivers that drilling, and we need equipment as well to produce the wells later on. In terms of data, we often work in a world that we do not have measurements every time we want some. So if you are drilling, you have to appreciate that the pore pressure fracture gradient often is given by models from the geologist team and subsurface teams as well. And based on that, we designed the entire drilling setup and the type of drills, the type of casing used, and then the cement as well to provide reliability throughout the life of the wellbore. And whenever data is missing, we have to rely on simulation tools. And what I will try to prove today here on the first part of the talk is that some of the simulation tools available in the oil field lack accuracy or even precision. So we might need to think a little bit out of the box in order to get that extra level of detail. If we're talking real-time data analysis, data needs to be available. Data needs to be transferred from the rigs to the office in central locations and perhaps be stored, be interpreted. So we need data management, we need data quality. Then we need tools that can process that data in real time or in almost real time. And because you might appreciate the tremendous amount of data that we're talking here, we can connect that to machine learning, to algorithms and computational power and CPUs and all of those big buzzwords around big data. And then, of course, if we are able to do a good job managing all of these concepts, we are in the world of a big prize here. We have self-verification, we are opening doors for new tools, new sensors, efficiencies, automation, acting versus reacting. It's basically the information era. It's the data. Digital is here to stay. So let's dwell a little bit more, as I was saying, in the job design. I will be showing 2 examples here using CFD tools. And in the first, I think it will be clear that some of the tools available do indeed do not predict results very accurately, and how can we mitigate that? In the second example, I'll give you a very practical case where CFD helps make some informed decisions. But let's start with this first example. On the first example, I'll be talking about the flow around liner hangers. This is a work that I did a few years back, and actually this was presented already in one SPE conference, or some detail of this work was presented on an SPE conference a few years ago. For those who do not know what the liner hanger is, it's basically a piece of equipment that has the objective of basically saving the amount of casing that you deploy in the hole. So it's a tubular structure that deploys the casing below it by latching itself to the previous casing, as shown here on the schematics. But then, because of this latching, this metal-to-metal connection, we are creating restrictions to the flow. And those restrictions will affect the flow and will affect the pressure drop as we displace cement or mud past it. But into what extent? That's the question that we will try to answer. Many of the tools that are available nowadays in the oil field world, they assume two things. They assume fully developed flow, and they use simplified eccentric tubulars to mimic the complexity of these geometries, the geometric aspects of this liner hanger. And those assumptions are not verified for flow around this equipment, as any other equipment that has a geometry that detaches itself from tubular, simple tubular. In this work in particular, I will be focusing a liner hanger that deploys a 7 5/8 inch liner on a 9 7/8 inch casing, so typical dimensions. And I will be comparing some experimental data, some simplified concentric pipe model, an eccentric pipe model, which is an example of a typical tools available in the market for the oil field, and computational fluid dynamics. Oops, clicking there on the wrong button. So in terms of experimental test, this was done in a yard facility from a service provider. Service providers was also involved, and basically we have a hole that was 200 feet deep. We deploy the casing with the dimensions that I just said. We deploy the liner hanger, and then we just basically let it flow mud around it or past it with those properties there. The mud would follow a Herschel-Buckley typical model. It was a water-based mud with a constant density of 13.3 ppgs. And we were collecting pressure drop, or let me rephrase that. We were collecting pressure values at the pump in the surface for different values of flow rates. This was the experimental, and as you might appreciate, this will be used as a reference point. So any other result that I'll be discussing here, we would like them to be comparable to this experimental data. The second approach that I will talk here is a simplified concentric pipe model. And if you know a little bit about fluid dynamics, there's a few reference books available. I just went to the Munson book. It's a Munson 2006. It's a book in fluid dynamics. And I took the Poisson law that can be described more or less, and for a given pressure drop per unit length, the volume rate of flow is inversely proportional to the viscosity and proportional to the tube radius to the fourth power. That's that equation you have there. This is a very simplified approach, as the name says it. It assumes incompressible Newtonian fluid. That again, we are detaching or getting away from the non-Newtonian aspect of the water-based mud that we're using in the experiments, and it assumes a fully developed laminar flow. Let's discuss that later on. The pressure drop is mainly from two contributions, the flow inside the liner hanger and the flow in the annular gap. We are fixing the viscosity to an equivalent Newtonian fluid viscosity. Very simplified geometry. Very simplified method of calculating the pressure drop. The second one that I will be talking and comparing against is the eccentric pipe model. That is a typical fluid simulator that was developed in the 90s. Many service providers, many operators, they rely on tools that were developed many years ago. Of course, there has been updates, but these still have some assumptions here. Simplified eccentric tubulars. For example, in the case of the liner hanger, instead of recreating the geometry in detail, we often play around with the diameter to create that restriction to the flow. And again, this simulation tool still assumes fully developed flow in the entire domain, but it might allow to use either laminar or turbulent flow regimes. If it's something in between, in a transient state, we won't be able to use this tool very accurately. The tool was, the model that we use here was for 200 feet, vertical well bore, same dimensions as the experimental, and we can accommodate a Herschel-Buckley model for rheology of the water-based mud and constant density as well. And finally, I will be comparing results against computational fluid dynamics. And here, I had the liberty to go ahead and do the details, the geometric aspects of the liner hanger itself, and those are captured there in that image that you are able to see in your screen. I used some commercial available CFD package. I used Fluent from ANSYS, and the geometry that I simulated, for the obvious reasons of having a time frame that was feasible to run the studies, was around 7.5 meters length, and it was simulated at a 1:1 scale. Even the simulation was only for 7.5 meters. It still created 2.5 or in excess of 2.5 million cells of about 1 to 3 millimeters each. Given the repeatability and symmetry of this geometry, only 1/6 of the structure was simulated. But again, because we're studying the pressure drop across it, it's still representative. The boundary conditions at the inlet were a mass flow and at the outlet a fixed outlet. I'm using a laminar formulation, so that means that I'm not using any averaging method to calculate turbulence if indeed turbulence exists. Density is constant, and the rheology also a Herschel-Buckley model. Let's compare some results now. In this first graph that I'm showing you here, you can see pressure as a function of the flow rate. And we have here results for experimental data in brown, CFD in green, the eccentric pipe model in blue, and the simplified concentric pipe model in red. Let me start by explaining why we have those oscillations on the experimental data. We use on the experiment some typical equipment from rigs, and we were using a pump that created some oscillations to the flow. That's why we see those, basically instead of having a smooth line, we have those points that have a confidence interval. But they are enough to capture that trend line there in brown, and it will be enough, I hope, to prove that there is an interval of confidence where we would expect the pressure drop to be as a function of flow rate. So now going to the simplified concentric pipe model, the red curve at the bottom of the image there, you see that because of the assumptions were perhaps too broad, we are enabled to capture the full pressure drop of the flow. If I can remember, if I remind here what were those assumptions, we were using Newtonian fluid and a fully developed laminar flow. So some of these two, one or at least, or both of these assumptions may not be doing the trick for us. If we increase the complexity of the model, that means going to the eccentric pipe model in blue, we see that for low flow rates, we have a good match for flow rate 1, perhaps 2 barrels a minute, but as soon as the flow rates increase and therefore the velocity, we are detaching from the experimental values. Again, if you remember, this model assumed fully developed flow as well, and perhaps the flow is not fully developed. If we go now to the CFD data, you see a match, and you see a trend line, at least following the same trend as the experimental data. There's a detachment here. It's not basically overlapping the experimental trend line, and the reason for that is simple. If you remember, the CFD was only using 7.5 meters worth of length of the liner hanger structure, whereas in the experiments we used 200 feet. But I will show you that perhaps, and it's worth considering that already, most of the geometry is smooth pipe. Only around the liner hanger structure we will have these geometries that kind of create obstacles to the flow. So I think with this result we prove quantitatively better saying, that CFD can be representative of the flow of the liner hanger. With that in mind, perhaps now we can compare a little bit more in detail pictures from experimental tests to the CFD results. And I will be showing you a couple of slides where you will have a picture from experimental data taken after the test and the path lines obtained from CFD. There's a color code here that is representative of the velocity. You can see here, for example, in this image, that we have zones that the flow recirculates. So, for example, here in the base of the slips, you see some streamlines, and streamlines is basically the theoretical path a particle of fluid would follow. That gonna go around. They are kind of running around itself. There's a little vortex here, and that creates what we call a dead volume. That creates a recirculation pattern that may develop to the point that you have material being left behind. And that's exactly what we saw here on the experiments. You see some accumulation of mud residue. And then you see, parallel to the slip zone, pretty well-defined parallel streamlines, means that the fluid is moving all the way up across this section here. And that creates this clear area, but also some level of high velocities that might induce erosion. On another picture, you see here that there's, on the geometry, there's like a bigger diameter on the liner hanger, and that creates an obstacle to the flow. There's a live edge here that you can see with that band in yellow on the picture, and that's represented here on the CFD. Well, sorry, let me point this. So that's the yellow band there that you see on the experimental picture is represented, or is more or less on this area here on the CFD image that I'm now pointing out on your screen. And this is a live edge. Basically, any fluid flow moving from up right to the left stop will hit that obstacle, and it will have to overcome that obstacle. So the velocity comes so close to a halt, and therefore pressure increases, and the streamlines have to go around the obstacle. Here, because we have a smaller diameter, we have a smaller cross-section area available for the fluid to flow. The fluid, of course, will have to accelerate because we're keeping the same flow rate. So we see those red lines, those accelerations, the velocity is quite high, and that creates this clear band. There is no mud left behind in that disc there. But after that high diameter zone, you see again those recirculation patterns. The fluid has again more cross-section area available to flow, and it doesn't know yet very well where it wants to go. The flow is not fully developed. You see these recirculation patterns, and with it again comes mud being left behind. Another issue as well, as I was saying with this acceleration, that creates erosion. And here on this picture where I'm pointing now, you see there a zone where this this yellow band was eroded away in more detail there. So this is an issue as well. So we're getting acceleration zones, deceleration zones, mud being left behind, and erosion. All of which there are some issues from the hardware standpoint. In summary, I think these results are clear to show that the flow regime is not fully developed because we've seen those vortex acceleration decelerations. The geometric details impact the flow field and therefore the pressure drop. And the CFD was validated experimentally, both qualitative and quantitative. With that in mind, then we can use CFD to understand a little bit more about the flow around or past liner hangers. In this image here, what you're seeing is a representation of the geometry used, but I split it in zones. And then for each one of the zones, I'm plotting or demonstrating here on this table what is the pressure drop as a function of flow rate. So for example, for zone 1, you see that as we increase the flow rate, the pressure drop increases with the pressure drop increases as a function of flow rate, which is all right. For example, here on zone 7, which is a piece of pipe where it's pretty much smooth, we see that the pressure drop increases with the flow rate very linearly, very little, so very smooth pipe. So that assumption that the regime here is fully developed might stick. But if you look to zones, for example, zone 2, where the slips are located, you see that the pressure drop goes from 16 psi at 1 barrel per minute up to 284 psi at 5 barrels per minute, which is quite considerable. Another interesting point here is that for zone 3, we see pressure drop that is negative. And at first, these results might sound curious, but if you think of it almost as a plane wing, that's how planes fly, right? So we have a suction zone. We have a zone where fluids flow at high velocity, and that creates a suction zone or a low pressure zone, and that eventually makes the plane able to fly. Same issue here. If you remember that zone there highlighted with number 3, that's where we had that acceleration zone. All those red lines of the streamlines were all red, so velocities in excess of 1.5 meters a second. And that means that we have this suction zone. To the extreme, you know, if this was a bigger zone, this could create stuff like differential sticking, for example. But let me ask you this. If you had to make an action, if you had to improve the geometry, what zone would you probably work on? And to me, the question is clear. I mean, looking to the data here, perhaps zone 2 is worth considering. Perhaps zone 2 is the zone that most affects the pressure drop when we are flowing mud across the liner hanger. Let's use CFD to go a little bit more in detail on the velocity distribution. And here I have two graphs that are histograms of velocity magnitude. So basically what I'm saying is what is the percentage of the domain in study divided or split in buckets of velocity magnitude. So, and that is presented here for two flow rates, 1 barrel a minute and 5 barrels a minute. Focusing on the 1 barrel a minute case, you see that most of the fluid is moving at low velocity. So 95% of the fluid particles will have a velocity comprised between 0 and 2.5 meters a second. The average velocity is roughly 1 meter a second, but we still see some zones in our domain that reach a maximum of 13.5 meters a second. Anyway, the flow regime is laminar, and the laminar assumption withholds. But on the 5 barrels a minute case, we see now that there is a more broadened distribution here of velocity. "95% of our fluid is now moving of velocities between 0 and 15 meters a second. The average velocity is now 5 meters a second roughly, but there are instances where fluid reaches up to 60 meters a second.
Учеба.
Учеба.
Что такое? У вас дичок был?
Да,
Что как? Защитился ли?
да.
Трудно?
Нормально? Он нормально был.
А что спрашивать вообще?
Он мало спрашивает один вопрос там. Что он делал? Там график как построил.
И все? Алло?
Бабка, да?
Ничего? Какой можно? Что, сегодня вечером что ли? Как хочешь. Уже не знаю, сейчас знаешь. Охота или не охота? А? Пойдем и все. Кофе. Пойдем и кофе. Пропусти чего? Чего пропусти? Ну, посидим там 20 минут. Работает, если что. Все. Так уж думаю. Пойду там сядь. Странно работает, тяжело. Сказать, что ну, мне и дома надо прийти. Переодеваться еще. У меня бюджет есть. Привезти. И привезу. Рубашку свою привезу на всякий случай. И еще какие-то KG jest takie. Poważnie? Podwodki? Na koniec. Nie. Мне еще и после 12 надо прийти, да? Страховой возьмешь, а то да. Сейчас перезвоню. Зачем мне жениться, а? Да? Зачем жениться надо? Что каждые 5 минут звонит. Ты где? Что делаешь? Ты с кем? Блин, я это не хочу как-то.
Зато вечером ты не один.
Это да. Это точно. Зато вечером есть.
Мне не забронировали, ладно.
Ладно.
Ты же мужчина. Надо кормить семью.
Конечно. Даже не себе только кормлю. Работать, работать.